In this video, I want to discuss what's perhaps the most famous theorem in mathematics. It's called the Pythagorean Theorem. All right, and it pertains to right triangles. And what it guarantees for us is that if you measure the lengths of the sides of any right triangle, all right, so you can do this yourself. Let's say the sides had lengths A, B, and C. You would notice that a squared plus b squared equals c squared. Go ahead and draw several right triangles of any size and shape on a piece of paper and measure the three sides and see if indeed this pattern is true. Okay? Some known lengths of right triangles that I could impress upon you are the following. So, if you drew right triangles such that the legs had lengths 3 and 4, you would notice that the hypotenuse has to have a length 5. If you made a different right triangle where the legs had a length 5 and 12, the hypotenuse, you'd notice, has to be of length 13. If you made one where the legs had length 1 and 1, so as isosceles, you would notice that the hypotenuse has to have a length root 2. Okay, let's see that indeed the Pythagorean theorem is satisfied for these three triangles. So convince yourself that 5 squared is equal to 4 squared plus 3 squared. Convince yourself that 13 squared is equal to 12 squared plus 5 squared. Convince yourself that root 2 squared is equal to 1 squared plus 1 squared. Okay? Root 2 squared is 2. Okay? 13 squared is 169. Does that equal 144 plus 25? Does 25 equal 16 plus 9? Okay, so those are three examples, and I invite you to try other ones. All right. Now, I said this was the most famous, possibly the most famous theorem in mathematics. The funny thing is Pythagoras isn't the first one to have discovered it or proved it. The ancient Egyptians knew it before the ancient Greek Pythagoras, and probably maybe people even before the Egyptians. Okay. There are over 100 proofs. Even the former Emperor Napoleon devised a proof. Okay, so there's no shortage of proofs. Sometimes people think that there's a, quote, right proof, when in actuality there could be several proofs to a given theorem. Okay, I'm going to show you what's perhaps the most simplest proof. Okay, so remember, we're trying to show that if you have a right triangle, sides A, B, and C, we're trying to show that a squared plus b squared equals c squared, where c is the length of the hypotenuse. Okay? Here we go. Fasten your seatbelt. So let's take our triangle with sides A, B, and C, and let's make 4 copies of it. Okay, and I'm going to put the 4 copies, I'm going to arrange them in a square in a certain way, and you'll see why in a second. All right? So I'm going to take one of the right triangles and I'm going to put it something like this, and then another one this way. Okay, something like that. All right, and actually, let's make the sides have to join. So actually, assume that I was able to make the perfect copies and arrange a square so that these red sticks come together. Okay? And just so it's clear where the triangles are resting in this square, let me color in the original triangle yellow. And then, so I have my copies here. Okay, and you can hopefully see if my picture is adequate. You can see that we have the hypotenuses are the red sticks, so those all have a length c, and we've got short sides with a length a, and then the long sides, long legs, short legs, long legs, I mean, that's what A and B are, the short legs and long legs. Okay, so there's, in my diagram with 4 copies of the original right triangle, I have a square, and what's the area of the interior piece of the square that does not contain any of the triangles? We know that the area of a square, or yeah, the area of a square is the square of any side length, so the area is c squared. Okay, now what I'm going to do is I'm going to take the same square, but I want to rearrange the 4 triangles a slightly different way. Okay, this time let's do this. All right, so the yellow triangles are the copies. I have 1 copy here, 1 copy here, 1 copy here, 1 copy here. So the lengths of my sides, I have here B, A, B, A, B, B, and A. Okay? So we know that the whole, the 2 boxes, the 2 holes, have to add up to the same area as the original big hole of area c squared. Okay? The area of the small box is a squared. The area of the bigger box is b squared. We said that the empty part on both squares had to be the same on the big squares. So therefore, a squared plus b squared, that empty part has to equal the empty part on the first square, which is c squared. So there you have it. A squared plus b squared equals c squared. Now, one way that this is useful, let me show you an example. Suppose that we had, here's the type of problems that you will encounter. Suppose we had right triangles and we didn't know one of the sides. Okay, so maybe you knew that this was 1 and 2, but you didn't know what side D was. Maybe you knew that this was 4 and 3, but you didn't know what side L was. Okay, you can solve, in both of those cases, if you have right triangles, you can solve for D and L. You can solve for the missing side. In the first case, D squared is 2 squared plus 1 squared. So D squared is 4 plus 1. So D is the square root of 5. Okay, using the Pythagorean theorem. Now in the second case, you have to be careful how you arrange the squares. You've got 4 squared equals 3 squared plus L squared. So L squared equals 4 squared minus 3 squared, or 16 minus 9, or 7. So L is the square root of 7.